You got it. Okay, let's try to get started. Is all good? You can hear me online also? That's good. Okay, if people online can hear me, that's good. You can see that this seems to be working. Lights are okay. Can people in the back hear me? Okay, great. Okay, let's get started. As you know, we covered out-of-order execution last week, which is really the cornerstone of how high-performance processors extract parallelism out of sequential code today. And it's beautiful, as you have seen. I'm going to wrap that up today first, and then we're going to talk about superscalar execution, which is an orthogonal concept. Sometimes people confuse these two things. When they talk about superscalar, they mean out of order. And when they talk about superscalar, they mean superscalar and out of order. But these are completely orthogonal concepts. You can have an in-order processor that's superscalar. You can have an out-of-order processor that's scalar, as you will see soon. But let's see where we are in the grand scheme of things. Basically, in the past several weeks, plus the Easter break, we've been talking about microarchitecture, and we're almost at the end of it. Today, we're going to cover Dataflow and superscalar and branch prediction. Probably branch prediction will continue till tomorrow, more advanced branch prediction. And I want to cover branch prediction because it's an example of how complicated existing processors can get. How many people watched the load store handling lecture? Anyone? Okay, no one, or maybe they're not here. I'd recommend looking at it. I mean, you won't have questions on the exam for it, but you will see that it's actually a tough part of the pipeline. That's the most complicated part, I would say. I would say branch prediction is less complicated, although there are algorithms everywhere. So if you look at what we've been covering so far, we've really been covering hardware algorithms. We didn't call them algorithms necessarily, except for Tomaslow's algorithm. But these are really algorithms that you bake into hardware. They're hardware-friendly algorithms in general. They're not the sophisticated, complicated algorithms that you may not be able to implement in hardware that easily. So we actually are designing algorithms to be executed, to be implemented in real hardware. And Tomaslow's algorithm was one of those. Okay, readings, we've talked about that. Let's review and wrap up out-of-order execution. So out-of-order execution, we simulate the machine. It's really all about four things: linking, buffering, tracking readiness, and dispatching. That's it, basically. So what do you link? You link the consumer to the producer, such that consumer can get the value. You buffer the instructions until they're ready, so that they don't really stall some other instructions. You track the readiness of instructions while they're being buffered, so that you can figure out what should execute next. And then when you figure out an instruction is ready to execute, you dispatch it to the functional unit so that it can actually execute. Basically, it's really all about these four things. And these four things, as you can see in the slide, are implemented or aided by different concepts or algorithms, if you will. Register renaming, for example, eliminates false dependencies and enables linking of the producer to the consumers. Buffering in the reservation stations enables a pipeline to move for independent or ready instructions without being hindered by non-ready or dependent instructions. Tag and value broadcast enables communication of values and the readiness of values between the producer and the consumer instructions. That's track readiness part. And wake up and select enables out-of-order instruction dispatch into the functional units. And that's the dispatch part. So basically, link, buffer, track readiness, and dispatch. You could potentially do these things differently, but that's not what we're going to cover. We've seen an example of how it's commonly done in today's processors. Of course, as I mentioned, there are lots of other optimizations that go into this, both algorithmic as well as implementation optimizations. We've also seen in the last lecture that out-of-order execution is really a restricted data flow concept. An out-of-order machine really dynamically builds the data flow graph of a piece of the program that is limited to the instruction window. An instruction window is all of the instructions that are decoded, but not yet retired. These are essentially the instructions that are in the reorder buffer. A fraction of these can be in the reservation stations also. So we've also proven this, right? Remember that I showed you that given the state of the register alias table and reservation stations in cycle 7, we could reverse engineer this data flow graph. This picture doesn't look like a data flow graph, but I showed you online how I could reverse engineer this data flow graph easily, if you know what you're doing, of course, if you know how the machine works. So that shows that out-of-order execution is really a data flow machine, but it's restricted clearly because it's not building the entire data flow graph of the entire program. It doesn't have that visibility because it doesn't have that many reservation stations or reorder buffer entries, right? Okay, we're going to get back to this. We're going to contrast this with the data flow concept at the ISA level. But you guys remember this, right? When I constructed this data or reverse engineered this data flow graph. This is actually fun. This is actually a lot of fun because it has implications on security also. If I can easily reverse engineer what's going on inside the machine like this, somebody can actually figure out how to attack your machine also with side channels, etc., because they can figure out what is executing on your machine potentially. So it could actually go much deeper if you really know what's going on in the hardware when the processor is executing programs. So I just gave you a glimpse of reverse engineering, but reverse engineering has a lot of implications on security. And today, security is a huge deal, right? If someone actually knows what you're executing on your machine, they could get to your privacy critical data, or even worse. Okay, so we also covered this slide, so I will not spend a lot of time, but basically, out-of-order execution has been successful because we combined it with another concept, another sort of algorithm, which supports precise exceptions, right? We talked about the reorder buffer. So most modern processors use reorder buffer to support in-order retirement of instructions. And we have a single register file, physical register file to store all registers. And there are two register maps that store pointers to the physical register file. One is used for at the front end, at the decode stage, to rename instructions. This looks at the speculative state of the machine. And the other is used at the end to keep track of the architectural state of the machine. It's basically architectural register map. These are actually register maps, which map the register numbers to locations and the values in the physical register file, because we don't want to replicate the values, if you remember what we discussed last time. Again, we discussed all of these, so if you don't remember, I will point you to the lecture last time. And this was the picture that we built, out-of-order execution with precise exceptions. Values are only in the register file. Everything else contains pointers to the physical register file. Okay, and then we discussed what happens. I'm not going to go through this again. If you have a machine like this, things change slightly in terms of when you access the register file, for example. And I said that this is actually employed in real processors. We had discussed the reorder buffer in Pentium 3 and how it works with the retirement or architecture register file in the reorder buffer lecture. But in the last lecture, we basically unified the values in a physical register file, just like Pentium 4 does. And you still have a reorder buffer to keep track of the status of the instructions. And I'll give you examples from real machines, just to jog your memory. I'll go through these relatively quickly because we don't have time. But I will remind you that this MIPS architecture that you're actually using in your labs, the mindset was, let's keep the hardware as simple as possible. But you can see that even they have succumbed to very quickly making the hardware more complex, because it's very difficult to extract parallelism out of code otherwise. We're going to talk about that. Actually, if we have time, we'll jump to VLIW processors tomorrow, which is a mindset very similar to the MIPS architecture. And we're going to talk about why it has not been as successful as well. So basically, you can see that there's a huge push towards making the hardware complex to extract parallelism out of the code so that you can execute independent instructions, because other ways are not working very well. Other ways burden the software in general. Okay, I'm going to skip through these slides because we already discussed this, but I added this picture, which kind of gives you an idea. But we're going to get back to some of these pictures when we talk about superscalar execution, because some of these pictures are actually useful for superscalar execution also. Okay, so let me jump into new material. These are things that we had on the slides, but we kind of skipped, but it's good to cover them quickly. Why is out-of-order execution beneficial? Can someone summarize with one or two words? What's the real benefit of out-of-order execution? You can use 3 or 4, it's fine. Anybody? Anybody who's bold, who's warmed up? Not yet? Should I summarize it? I guess so. If I'm not, yes, please. That's good. Yeah, avoiding stalls. It's, I think the way you described it is good, it's correct. But But how do you avoid stalls? It's not getting into that. So how does it avoid stalls? That would be my next question to you. Okay, maybe I'm expecting too much right now on the online. But basically, it does avoid stalls by tolerating latencies. So I would say latency tolerance. Basically, tolerates out-of-order execution tolerates the latency of multi-cycle operations by executing independent operations concurrently. This may be a mouthful, but it's good to think about what happens if all operations take a single cycle. If all operations actually take a single cycle, out-of-order execution's benefit is almost zero, essentially, because you can tolerate all of those latencies relatively easily. Okay, you should think about this probably if you want to know more. So what if an instruction takes 1,000 cycles? Let's actually take the latencies to the extreme. How large of an instruction window do you need to continue decoding without stalling? Basically, about 1,000 cycles, basically, about 1,000 instructions if you're fetching one instruction per cycle. Then the question also becomes, how many cycles of latency can out-of-order execution tolerate? Tolerating means basically avoid stalls. So we're going back to that. So you're actually correct in the sense that tolerating means you keep decoding without stalling, essentially. So in the end, I think you were very close. So basically, the question is, what limits the latency tolerance scalability of Thomas Low's algorithm? And the answer to this is the size of the instruction window, right? How much hardware can you build? How many decode instructions you can keep in the machine, but that are not yet retired? So that's the size of the instruction window. So if your latencies grow, they become 10,000 cycles, you need to have a 10,000, approximately 10,000 entry instruction window to keep going, basically, without stalling. Now, this doesn't mean that you'll find independent instructions, but empirical evidence shows that you can actually find independent instructions if you go further in the code. Not all code has lots of independent instructions, of course, right? You can imagine a linked list traversal where you have a lot of dependencies. Okay, so these are some questions to ponder, basically. We're going to get back to that later on, perhaps. But now let's conclude out-of-order execution with the trade-off. So what are the advantages? Basically, we just said that. Out-of-order execution allows independent instructions to execute and complete in the presence of long latency operations. So it gives you latency tolerance. As a result, it gives you higher performance than in-order execution, significantly higher performance. Another way of looking at it is it enables you to exploit irregular parallels. Now, what does this mean? Basically, you have some code that's sequential. You can dynamically find which instructions can be executed in parallel. You can dynamically pick and choose. Now we're going to see that, we kind of saw that when we talked about software scheduling, right? Software can schedule instructions that can be executed, not necessarily in parallel, but that can be executed without dependencies. We talked about code reordering. We're going to talk about that more. Out-of-order execution does that in hardware, but it doesn't have the downsides of some of the software because it can do that by really knowing which values are ready. Whereas if at the software level, you don't know that information. And we're going to see that when we talk about VLIW processors tomorrow or next week. Okay, does that make sense? Okay, so disadvantages, of course, higher complexity and higher hardware cost. So that's what we've been doing all along, actually, for the past several weeks. We've been trying to get higher performance at the expense of higher hardware cost. So there's no free lunch. The performance that we're adding to our machines are coming at a cost, which is higher complexity. In fact, some of these loops that we discussed yesterday can potentially lengthen the critical path delay, can affect the clock cycle time. So your clock cycle time may be longer than an in-order machine. To avoid that, people pipeline out-order machines more heavily. And then more hardware resources needed, like we discussed, right? Reservation stations, larger instruction windows, the tag matching logic. Those are the most complicated parts of the machine, basically. The huge buses that you need to drive across the entire, let's say, window where you need to schedule instructions. So basically, just like every other idea that we examine, there are trade-offs over here. So recall the execution time of an entire program. What out-of-order execution does really well is, assuming we don't change the instructions, we don't change the program, basically it reduces the cycles per instruction because it increases the throughput of instructions. You can schedule more instructions in parallel. You're overlapping the cycles each instruction takes. So you're really increasing instructions per cycle, which is reducing cycles per instruction, which is the inverse of instructions per cycle, right? But this could actually increase your clock cycle time compared to an in-order processor. Does that make sense? Now, you could keep the same clock cycle time compared to an in-order processor by pipelining more. Now, by pipelining more heavily, unfortunately, pipelining more heavily increases your average CPI because of what we will talk about next, branch mispredictions, for example, or the dependencies. So there's a trade-off that you're really trying to balance over here. Out-of-order execution hopefully is increasing or reducing your CPI significantly and impacting your clock cycle time a little bit, perhaps. To overcome the impact on the clock cycle time, you're pipelining a little bit more heavily, which is increasing your average CPI. But hopefully, the benefit you get by parallelizing instructions using out-of-order execution, the reduction in CPI you get is larger, much larger than the increase in CPI you get because you try to keep the clock cycle time the same as a equivalent in-order processor, let's say. Hopefully that makes sense. So this is actually, this performance equation is very interesting to think about. Okay, so if you think out-of-order execution is complex, you should watch the load store handling because that's even more complex. But I'm not going to talk about that here. Any questions? Otherwise, I'm going to discuss data flow versus out-of-order execution a little bit, and then we're going to talk about superscalar execution, and then we're going to jump to branch prediction. So after branch prediction, we're going to cover a lot of other approaches to extracting concurrency or instruction level parallelism from programs. So if you think about it, pipelining is really parallelizing instructions, right? You have one instruction in one pipeline stage, another instruction, another pipeline stage. You're really overlapping the latency of instructions, right? To increase the throughput of instruction processing. So that's one approach to actually increasing concurrency in your machine. And that's why it improves performance. Fine-grained multi-threading, we've also seen that as an example of improving concurrency. It doesn't help a single thread. It actually hurts a single thread, but it really helps the throughput of the entire threads if you have many threads in your machine. We talked about out-of-order execution. That also parallelizes instructions because it executes multiple instructions in parallel. And that enables also instruction-level concurrency. So these are really approaches to instruction-level concurrency that we've been uncovering, if you will. If you look at the single-cycle machine versus multi-cycle machines that we developed early on, they're very primitive. There's no concurrency between different instructions, right? In a multi-cycle machine, we finish one instruction before we start the next instruction. But all of these, at least the ones that you know at the top, are different. So in the next, after we cover data flow and superscalar today, in the next lectures, we're going to see a lot of these other approaches to instruction level concurrency that are actually quite different from out-of-order execution. Some of those are employed actually in many systems, like GPUs employ single instruction, multiple data parallelism. And many machine learning accelerators employ systolic arrays, as we will see. So these are also quite impactful. But let's talk about data flow, because we said that out-of-order execution is actually a restricted data flow machine. But data flow at the ISA level we have seen. And I want to make a point by quickly talking about it. I've already covered this basically. Out-of-order execution builds a small part of the data flow graph of the entire program. And we've kind of proven it. But if you remember data flow, in data flow, availability of data determines the order of execution of instructions, right? And a data flow node fires when its sources are ready. And we, if you remember lecture, I don't remember which lecture it was, 9 or 7, one of those. A data flow, basically we express programs as data flow graphs at the programmer level. Now this is nice, of course, at the programmer level, but it's asking too much from the programmer. Basically, asking the programmer to represent their programs as data flow graphs has not been very successful because it requires everything in the software stack to change if you're used to single thread programming, especially von Neumann model. So we contrast the data flow versus von Neumann, right? So it's fundamentally different. As a result, this has not been successful. People tried it a lot. 1970s, 80s, 90s, early 2000s, they gave up basically. I don't know of anyone trying to build a data flow machine today. But, and one of the reasons is people figured out how to do this without disturbing the programmer. And that's out-of-order execution basically. So we've seen that out-of-order execution is a restricted data flow model. And that it's really an implementation of data flow at the microarchitecture level that preserves the von Neumann model semantics, sequential instruction processing. And as a result, it has been very successful. I think there's a lesson here which says that if you really want to build new hardware that's going to change like improve performance, ideally you should do it without disturbing the programmer. Meaning, don't ask the programmer to rewrite their code, ideally, if it works. If you ask the programmer to rewrite their code completely, if it changes the software stack completely, compilers, operating systems, programs, everything, which Dataflow at the ISA level does, it's probably not going to happen. And if someone figures out actually how to apply similar algorithms without actually burdening the programmer, they could be extremely successful. So Intel, for example, as a company has been extremely successful because they actually employed out-of-order execution. They built the first commercially successful out-of-order execution processor, Intel Pentium Pro. And they actually have been riding on that curve for a long time because nobody was able to compete with them in building these machines, at least as well. Things have changed, of course, recently. Okay, so out-of-order execution is a prime example of this, but there could be other implementations, that is Dataflow implementation under the hood. There's also one more thing I should say. More recently, because of the difficulties in scaling hardware as well as the programs, people have been using FPGAs, field programmable gate arrays, and they actually turn the program into a Dataflow graph, at least part of the program, and map it directly into hardware. There's no instruction set architecture over here. You basically turn part of your program into hardware logic and map it directly into an FPGA, into reconfigurable logic. So part of your program directly executes in hardware, basically. You call a function that does, for example, I don't know, video compression. Video compression is completely done using logic. There are no instructions involved. You basically says compress this video, and your FPGA does that. So this is another example of Dataflow model, because usually the way these things are programmed is programmer expresses the function that they're going to offload to the FPGA or implement in hardware purely as a Dataflow graph. And that Dataflow graph gets translated into circuits. Very similarly to what we have seen earlier in Boolean logic, basically. You can express Dataflow graphs as Boolean logic. And that Boolean logic can get implemented in gates in hardware in FPGAs. So these are actually connecting a lot of things that we have seen, but we don't have time to cover this one. But people have been doing this, and this is also becoming been very successful recently, at least in special cases. For example, people have been accelerating machine learning workloads on FPGAs using this sort of, some important machine learning kernels can be executed on the FPGA. Okay, this is another picture. I guess lecture 9 was the right lecture. We've covered this, if you remember. I mentioned there's an ISA level trade-off when we're designing an ISA. Do we want a program counter in the ISA? If you say yes, then you fundamentally say you have a control-driven sequential execution. If you say no, then one option is Dataflow, right? And we discussed this. So I'm not going to discuss this again, but this is just to jog your memory that we have covered Dataflow at the ISA level. Now, at the ISA level, if you have Dataflow, you can actually get even more parallelism, perhaps. Because hardware at the microarchitecture level is trying to discover a lot of parallelism that could be expressed by the programmer, right? If you actually express your program as a Dataflow graph, as a programmer, you can actually express that irregular parallelism, and you can optimize your Dataflow graph. So there's a big advantage of actually raising the Dataflow to the ISA level such that the programmer handles it. You can get much better parallelism because the programmer, if they work hard enough, they could figure out which things are dependent and independent, what could be scheduled separately. And so as a result, more parallelism can be exposed than the von Neumann model, so you could get a higher performance machine. But this has a lot of disadvantages, as we have discussed also. Basically, one of the biggest disadvantages is no precise state semantics. If you have a Dataflow graph, it's very hard to figure out where you are in the execution of a program when you get an exception or an interrupt, or when you want to do something to maintain the machine. So when you get a power, for example, when you're having power failure, what part of the program has executed and what part of the program did not execute? You have to record that somewhere, right? So that you can restart the program after the power failure. Recording that is very difficult because you have a huge Dataflow graph, potentially millions of nodes. It could be even larger, billions of nodes. You need to figure out which edges have executed, which edges have not executed, which parts have tokens, which parts don't have tokens. Tokens meaning readiness of the values, right? Which values are ready, which values are not ready. So it's basically a huge mess. That's why von Neumann model has been very successful. It doesn't basically, it basically has one instruction, and after that instruction, everything is not executed, and before the instruction, everything is executed, right? That's the precise state semantics. So basically, debugging is very difficult, and interrupt and exception handling and restartable programs is very difficult if you actually do data flow at the ISA level. On top of this, you get very large hardware overhead, because we've seen the hardware overhead in out-of-order execution machines. If you actually build a data flow machine at the ISA level, it's much larger. Of course, you can constrain the hardware overhead by making the data flow graph that you execute smaller, but then it basically takes a lot from the advantages. But usually people, when they try to build data flow machines, they had very large hardware overheads so that they could execute data flow graphs of millions of nodes. Now, okay, maybe you somehow bite the hardware overheads, but once you actually build that hardware, it also turns out that sometimes you have too much parallels. So these data flow machines had difficulty in controlling the parallels because there are many instructions that are ready at the same time, and scheduling becomes a problem. Which instruction do you dispatch to the functional units? We had that problem, if you remember, in out-of-order execution engines yesterday, right? Not yesterday, last week. 2 instructions became ready at the same time. And if 2 instructions become ready at the same time, you need 2 value and tag buses that go all over the place. Or you have 1, which restricts your parallelism, and you arbitrate for it. So in either case, you had extra complexity. Now imagine tens of thousands of instructions becoming ready at the same time, which could happen in a large data flow graph, like 1 million or millions of nodes. How do you deal with that? And this was a real problem when people actually tried to build data flow machines. And then there are other issues like software data structures, which I'm not going to get into, that were problematic. So it's fascinating, basically, but once you try to change things at the ISA level, it becomes very difficult, basically. That's the takeaway. And remember, this slide, actually, we've also seen, like when we talked about data flow versus von Neumann, we said that control versus data-driven execution can be made at the microarchitecture level. Instead of changing the ISA, we could just change the microarchitecture. Because microarchitecture can execute instructions in any order, as long as it obeys the semantics specified by the ISA when making the instruction results visible to software. That's what out-of-order execution with precise exceptions is, basically. And that's why that's been successful. Okay, so I could talk more about data flow, but I don't have time. There are a lot of interesting issues over here. They're a bit old, but a lot of these are actually applicable if you go and program FPGAs. If you want to actually accelerate your program by taking advantage of the FPGAs that you're using in your labs, you're using the FPGAs to model a microprocessor, right? You're using it in a different way. You're not using it to accelerate a program. But there are other uses of FPGAs where you can accelerate a program. What you're doing is really, you're using the FPGA as an emulation infrastructure to model the microprocessor, a general purpose von Neumann processor, right? But there are other ways of using it, like accelerating programs. And if you know about data flow, you'll actually be probably very successful in that. Any questions? Okay, I'm talking very conceptually today. We're going to go to less, let's say, examples and less conceptual things in superscalar execution right now. But I wanted to finish out-of-order execution and data flow discussion this way, because there's a lot there, actually, a lot more. Okay, so let's talk about superscalar execution. This is another concept that's heavily employed in all modern processors, basically. And it's a much simpler concept. The idea is basically fetch, decode, execute, and retire multiple instructions per cycle instead of single instruction. So far, we've been talking about single instruction fetch, right? When we're fetching single instructions. But why don't we fetch more than one instruction? And if you fetch more than one instruction, it makes sense to decode, execute, retire more than one instruction. This could increase your concurrency again, right? Ideally, it multiplies your performance by n if you can fetch n instructions per cycle, right? So it's very powerful. So basically, n-wide superscalar can fetch, decode, execute, and retire n instructions per cycle. Today's machines are about 8-wide superscalars, depending on what machine you're using, but 8 is a good ballpark. Something is happening here. Okay, everything's okay on the live stream, right? Okay. So of course, to be able to do this, you need to add the hardware resources for doing so. Again, this is a performance hardware trade-offs, performance cost trade-off. In order to increase performance, you need to add more hardware. So hardware also needs to in addition to providing hardware so that you can fetch, decode, execute, retire multiple instructions, essentially you need to have multiple concurrent pipelines, right? And we're going to see that in the picture soon. But you also need to perform dependence checking between instructions that are fetched in the same cycle or decoded in the same cycle. So far, we've been doing dependence checking in the horizontal dimension, right? Meaning you fetch, decode, execute, let's say, fetch, decode, execute, write back. That's the horizontal dimension. And you need to perform dependence checking between an instruction that's older than you and the instruction that's being decoded. But now we also have another dimension, which is the vertical dimension. We're fetching multiple instructions per cycle. And you need to do dependence checking between the instructions that are being fetched concurrently, right, or decoded concurrently. So you need to perform dependence checking both in the horizontal dimension as well as the vertical dimension between instructions that are concurrently fetched. Okay, so we're going to look at that soon. I'm not going to show you the dependence checking logic exactly, but you could imagine what that is. It's very similar to the dependence checking logic that you have in the horizontal dimension, but you have to do it vertically, meaning in the same cycle. You have to check the dependencies between instructions that are fetched in the same cycle. And that's clearly going to lengthen your critical path, actually. So people actually pipeline more to reduce the critical path increase because of this. But before I move on, I should say that superscalar execution and out-of-order execution are completely orthogonal concepts. Basically, if you have in-order, out-of-order on the one axis and scalar and superscalar on the other axis, scalar meaning you fetch, decode, execute, retire one instruction per cycle, you could have all possible combinations. You could have an in-order scalar machine. That's what we've been doing kind of so far, right? Well, until we got to out-of-order execution. You could have an out-of-order, you could have an in-order superscalar machine. That's what machines used to be before we moved to out-of-order superscalar. You could have an out-of-order scalar machine and out-of-order superscalar machine. You don't normally see out-of-order scalar machines that much because of the historical evolution of things, and it makes sense to actually exploit concurrency, both using out-of-order as well as superscalar execution. But all of the other combinations exist in the world. Okay, and don't make the mistake. Actually, the book that the paper that I recommended to you makes that mistake, kind of. The title of the paper is The Microarchitecture of Superscalar Processors, right? It's basically using the word superscalar as an all-encompassing term of existing processors. I would retitle that as the microarchitecture of modern, let's say, out-of-order superscalar processors, because it's missing the out-of-order part in the title. Okay, so let's take a look at an in-order superscalar processor. And you can imagine what an out-of-order superscalar processor looks like after you see the in-order one. So basically, this is an in-order superscalar processor. Whenever I fetch an instruction, I don't fetch an instruction, I fetch two instructions. Let's say two consecutive instructions. And then I decode two consecutive instructions. Basically, I doubled everything. You can see that I'm fetching two instructions. I've doubled the ports to the register file, so I'm reading 4 registers instead of 2 registers. And I have the ability to write 2 registers, as you can see. I have 2 ALUs to make sure I can execute 2 instructions concurrently. And I have 2 data memories or 2 ports to the data memory. I can read 2 things from the memory, 2 independent, completely independent things. And then I can write 2 results to the memory or the register file, as you can see. So basically, I've doubled all of my resources in the pipeline or ports. So clearly, this is a hardware cost. Ideally, the IPC instructions per cycle should be 2. Ideally, you should fetch, decode, execute, retire 2 instructions per cycle, right? Unfortunately, dependencies reduce this, right? Dependencies make it tricky to dispatch multiple instructions in the same cycle to the functional units. So we're going to see an example soon. So that's why you need dependence. Well, first of all, to make sure this works correctly, you need dependence checking between instructions that are fetched concurrently. Just like we needed the pipeline to work correctly, we needed dependence checking. The same thing is true here. So nothing has changed in that sense, except we're doing things vertically in the same time. Before, we were actually doing things in space, horizontally. Now we're actually in the same time slot, we're fetching more instructions. So we need to actually account for that as well. So let's take a look at this code. This code is constructed to be nice, let's say. If you have a 2-byte superscalar machine, this is the execution of the instructions, basically. Fetch, we have 5-stage pipeline in this case. And there are no dependencies between instructions that are consecutive. So this add is not dependent on load. So that's nice. They can go together concurrently until the end of the pipeline. There are no dependencies between sub and AND, so they can go together. There are no dependencies between OR and stored so they can go together. So in this case, actual IPC is 2 because in 3 cycles, you're issuing 6 instructions. So this is good. But life is not always this nice. As you know, we've covered dependencies many times. So if your code happens to be like this, the instruction after add is a load, and add is, no. The instruction after the load is an add, and the add is dependent on the load. You need to detect this dependence when you're decoding both instructions, and you need to make sure that this add doesn't go while the load is continuing. And this add needs to wait until load produces its value, right? Assuming that it produces its value in the next cycle, it can basically, this add can be scheduled, right? This is an ideal scenario, of course. So basically, here, even though we could have decoded 2 instructions per cycle, we couldn't continue one of them because one of them is dependent on the prior one that was fetched at the same time, okay? So that has to go in the next cycle, basically. So you need to have logic to make sure that dependent instructions wait until the next cycle. In this case, we don't have out-of-order executions or we don't buffer them. So the pipeline, the entire pipeline stalls, okay? So you can actually go through this yourself. This is actually from your book. You can find this in your book also. But basically, now what we have done is we have 6 instructions over here. Ideally, we should have finished them. We should have fetched all of them in 3 cycles. But we're issuing them in 5 cycles, actually. Yeah, basically it takes 5 cycles to issue them. The actual IPC is 1.2, basically. So if you really want to restore the IPC to 2, you need to reorder the instructions, and I'll let you figure out what you reorder. So the compiler, for example, can do some reordering so that this load instruction can be dispatched together, or this next instruction after the load can be dispatched together with the load instruction. And can you guess which instruction it is, just by looking at this code? Anybody? I would vote for this OR instruction. This OR instruction is not dependent on any prior instruction, right? So if you actually, if the compiler takes this OR and puts it after load word, you're back to 2 instructions per cycle. So that's the good part. Okay, so basically, you can use the compiler to take advantage of a superscalar machine in a better way, just like we use the compiler to eliminate the bubbles in a pipeline. You can think of the bubbles, this bubble over here, the fact that you cannot dispatch this instruction. It's really a bubble in the vertical space, right? As opposed to horizontal space. So basically, all ways of handling control data flow dependencies apply over here also. And we've seen a lot of ways of handling flow dependencies. You can also employ these in superscalar processors. So we employ them in pipeline processors. You can also employ them in superscalar processors. I'm not going to go through these clearly, but we're going to see one of these later on when we talk about bench prediction, or not how to not do bench prediction. Any questions? Everything's okay? Okay. So let's cover the advantage and disadvantage of superscalar execution. So hopefully, conceptually, this is very simple. Now you can see that if you have an out-of-order processor, you can also make it superscalar. You just fetch, decode, rename multiple instructions per cycle, basically. And the rest of the out-of-order engines operates similarly to what we discussed yesterday. And the big advantage is you can multiply your instruction throughput. And ideally, you multiply it by n, right? And n is a big value. Unfortunately, you're bound by dependencies. So higher IPC is instructions per cycle. As a result, you get lower CPI, as we discussed. And remember, basically, you can reduce your average CPI. But it comes at a trade-off, which is also going to affect the clock cycle time here. Basically, you need higher complexity for dependence checking vertically in the same cycle, as we discussed. Requires dependence checking between concurrent instructions. Register renaming becomes more complex in an out-of-order processor because you need to rename the registers sequentially in the same cycle. So if you're fetching 8 instructions per cycle, you need to rename the oldest one first, and then the next one, because next one may be dependent on the oldest one, and the next one may be dependent on both of the previous ones, and the next one. So renaming becomes a very sequential process, essentially. People try to actually pipeline it with various methods. And as a result of this, you potentially lengthen the critical path delay. So this is another example where you have an algorithm or technique that can improve your instruction throughput by reducing the average CPI, but it has adverse effects on your clock cycle time, right? On top of this, you need more hardware resources, as we've discussed, right? Clearly, you need to have multiple ports to your register file and memory. You need to have multiple multiple instruction fetch, which actually complicates things, as we will discuss in branch prediction. So there's a lot more complexity that you add just by fetching n instructions. So it's not just fetching n instructions, as you can see. Okay, that's it. This is an idea that's employed even before out-of-order execution. So this is Intel Pentium, which is earlier than Pentium Pro. This was able to fetch 2 instructions per cycle, basically, which is good, right? 2 instructions per cycle. By the way, the first machine I had was an Intel 486. Does anyone know what an Intel 486 is? Okay, no one knows because it was earlier than Pentium. Intel later. Pentium was supposed to be 586, but Intel decided their marketing strategy can become better if they actually called it something else. And they actually did a great job. They moved to Pentium. But 486 was the first pipeline machine of Intel, as far as I know. And then they added Superscalar execution. You can see that you can actually have 2 fetch engines. It's not shown very well over here. Basically, you can fetch, decode, execute 2 instructions per cycle. And then they converted this machine to, well, similarly around the same time, Alpha had in-order superscalar, 2 integer and 2 floating point fetches. And Intel decided to upgrade their machine to out-of-order superscalar. Once you have in-order superscalar, you just add out-of-order machinery to it. And similarly, Alpha also decided to upgrade their machine to out-of-order superscalar. And then because of, let's say, poor business and software compatibility decisions, Alpha dropped off the, let's say, competition. As a result, Intel was the only, with the exception of AMD, which was very small at the time. Intel was the only, let's say, biggest vendor at the time. Okay, later Intel developed this Pentium 4, which are basically out-of-order superscalar. And essentially, all major processors are out-of-order superscalar today. And again, you have this picture from your recommended reading, which should really say out-of-order superscalar processors. Okay, so you can see that this is AMD Zen. What do I want to point out over here? Clearly, there's a lot of complexity over here, but you can see that it's fetching and decoding 4 instructions per cycle. Internally, it's converting those 4 instructions to 6 micro operations. These are actually smaller instructions. Conceptually, like less complex instructions. So this is the hardware translator, basically. There's a hardware translation engine over here that's not shown. And then there's a huge execution unit, as you can see. This is the out-of-order part. And you can read more about it if you're interested. And you can see, according to reverse engineering people who are enthusiasts, Apple can decode 8 instructions per cycle. So it's 8-byte superscalar. These are different instructions. These are ARM instructions as opposed to x86 instructions. So they're simpler to decode, let's say. And you can see that the backend of the machine is actually pretty complicated, which I'm not going to talk about. But existing machines are out of order and superscalar today. And that brings us to the end of the lecture 16A. Any questions? Okay, if there are no questions, then we should take a break until 15:10. And then we're going to start with a branch prediction. Okay, let's get started. Now that we finished our break a little bit late. I should also mention that I had good discussions with some of your fellow students about FPGAs and other stuff. Apparently there's a career fair going on and there are people looking for FPGA engineers who can accelerate stock market programs or things like that. So this is actually, FPGAs are actually used in financial markets quite a bit because you can offload a computation and perform it extremely fast on an FPGA so that you can do things in a very latency critical manner. So that's one use case for FPGAs. And some of your other fellow students actually are able to display videos on FPGAs by doing video decoding, for example, something I mentioned earlier. So you can, even with your small FPGA that you have, you can actually do a lot of interesting things. Okay, just want to say that. But let's move to branch prediction right now. This is another fascinating topic. And this is actually one piece of the puzzle. If you want to make an out-of-order superscalar processor work, you really need good branch prediction. If you don't have it, forget about building it. And hopefully I will convince you why with one particular slide. I will mention that slide a little bit later. But we're at the end of out-of-order superscalar execution. We're going to finish it tomorrow. Probably we won't finish branch prediction today. But we're going to talk about control dependence handling. And we've kind of talked about this, so I'm going to go through some of these parts relatively quickly. Remember in lecture 13 that Mohammed delivered, we asked the question, what should the fetch PC be in the next cycle? You're fetching some instruction in the current cycle, you know the PC, but what should the fetch PC be in the next cycle in a pipeline processor? And the answer is, of course, address of the next instruction, right? But that's not an answer, or that's not a good enough answer, let's say, because what is that? What is that address? What should that address be? And all instructions are actually control dependent on prior ones because of the von Neumann model. The next instruction's address, assuming it's the next sequential instruction, is PC plus 4 in MIPS. In x86, the next instruction's address is PC plus instruction size. What is instruction size? It's not 4 in x86. It depends on the instruction that you're just fetching. Instruction size can be anywhere between 1 byte to 16 bytes in x86. So you first need to decode that instruction to figure out what the size is. So immediately in the pipeline, you have a problem if your ISA is like this. Even if you want to fetch the next sequential instruction, you don't know what that address is before you decode instruction. And when do you decode the instruction? The instruction moves to the next stage. Too late, because you should fetch the next instruction while there's other instructions, the decode stage, right? So basically, we have a fundamental problem in pipelining. You really need to know the address of the next instruction. And if your ISA is not nice, you don't even know that while you're fetching the instruction to keep the pipeline full. Okay, so if the fetch instruction is a non-control flow instruction, as we said, next fetch PC is the address of the next sequential instruction, and there are complications here. MIPS is nice because it's PC plus 4. So it's easy to determine if we know the size of the fetched instruction. But if the instruction that's fetched is a control flow instruction, you have even bigger problems. Basically, how do you determine the next fetch program counter? In fact, how do you even know whether or not the fetched instruction is a control flow instruction? You haven't decoded it yet, right? So technically, that pipelining immediately causes problems. Let's take a look at some of these branch types that are in real instruction set architectures. So there's some branch types that are easy, as we have also seen in our pipeline or even other machines. So there's an unconditional branch. It's always taken, and the number of possible fetch address, next fetch address is 1. And you can actually figure out the address at the decode stage. So even this causes a problem, but it's less problematic. You could have a call to a function. It's always taken. This is unconditional also. Next fetch address is only 1. And you could also figure this out and decode in general cases. So these are relatively easy. The harder part is conditional branches and returns and indirect branches. The hardest ones are actually the first one and the last one. So conditional branches, this is a conditional branch like we have seen BEQ, for example, in MIPS. The direction at fetch time is unknown. You have to execute the branch to figure out whether this register is equal to this register, right? So you have to wait until late in the pipeline. How long do you wait? Depends on the pipeline. If it's an out-of-order machine, it could be many, many cycles, hundreds of cycles, right? Because this branch may be dependent on some other instruction that's going to execute, and eventually you get to this branch. So basically, the execution, the next fetch address is register dependent, and there are two possible fetch addresses. One is the fall through path, which is the next sequential instruction after the conditional branch, and the other is the target, because you have an if, then if the condition is true, you jump to some other place in the code, that's the target instruction. If the condition is not true, then you go to the next sequential instruction, right? So there are two possible fetch addresses. Returns are always taken, so these are unconditional, but you need to figure out where to return after a call. So this is also resolved at the execution stage. We have seen return instructions also earlier. This is register dependent. Indirect branches are also always taken. We've also seen examples of this. Basically, you jump to a register, for example, jump register instruction in MIPS is an example. But then there may be many possible fetch addresses depending on the register value, right? And this is also resolved at the execution stage. So basically, the first one and the last one are the hardest. Returns are a bit easier if you actually are following the calls. I'm not going to talk about that, but existing machines follow the calls and use the predict returns relatively easily. But conditional branches as well as indirect branches are very difficult to handle because you need to predict the next instruction that's coming. And that's what branch prediction is all about. Okay, so different branch types are actually handled differently in the machine. We're going to mostly focus on conditional branches. Now, of course, you can say, what about conditional indirect branches, right? You could have even more complicated conditional indirect. Well, fortunately, they don't exist in many ISAs. So people basically figured out they don't want to complicate the ISA more. Okay, so basically, how do we handle control dependencies? It's critical to keep the pipeline full with correct sequence of dynamic instructions. We've also already seen this. We're going to see this even more. There are many potential solutions if the instructions are control flow instructions. Some of these also handle non-control flow cases as well. So we're going to look at 6 solutions. One is stalling the pipeline, which is clearly a bad idea, right? Until you know the next fetch address. It's a bad idea. We're going to predict branches. We've seen examples of this. We're going to see more sophisticated examples of it. Basically, branch prediction is guessing the next fetch address. While you're fetching an instruction, you're guessing what is the next fetch address. Okay? You can employ delayed branching, which is a bad idea. Hopefully, we will get to it. I'm going to talk about that. MIPS architecture actually has that, so you kind of ignore that for now. It's an unfortunate decision in the ISA. Do something else. We've seen fine-grained multi-threading. We're going to look at that. You've seen that already. Basically, avoid the problem, basically. Switch to another thread. Eliminate control flow instructions using instruction in the ISA. Hopefully, we're going to talk about that. And fetch from both possible paths. So if you actually have a branch, why don't you actually have 2 pipelines? One of them executes the taken path and the other one executes the not taken path. And eventually you figure out which one's correct and flush the wrong one. And people employed this idea, but it's not very hardware friendly, let's say. So what's employed in today's systems is branch prediction, a lot. Branch delay slot, unfortunately, let's say, even though it doesn't help. We're going to discuss that. Fine-grained multi-threading is heavily employed in GPUs, for example. Predicated execution is somewhat employed. Multipath execution is less so. Stalling the pipeline is not a good idea. Then don't have a pipeline, basically. So basically, let's take a look at stalling the pipeline. Stall fetch until next PC is known. Is this a good idea? Basically, I'm not even going to talk about conditional branch instructions or indirect instructions. We're just going to look at non-control flow and unconditional branch instructions. If you stall the pipeline until you really know the next fetch address, you should not be fetching in the next cycle. Because you really know the next fetch address after you decode the next instruction, right? That's true. Because you know that this is an unconditional jump over here, for example, and the next fetch address is the target of the unconditional jump. Okay, otherwise it could be PC plus 4. So basically, if you stall the pipeline, even ignoring the control flow instructions, you stall for 50% of the cycles, your pipeline immediately goes to 1/2 of its throughput. It kind of defeats the purpose of pipelining, basically. Don't do this. Okay, so we eliminated the first option. Let's talk about fine-grained multi-threading, which is a great idea if you can afford it in multiple ways. basically, remember the idea, each pipeline stage is an instruction from a different, completely independent thread. As a result, you don't need any dependency checking logic. No control or data dependence handling. So what does it mean to afford it? You need to be able to afford it in terms of cost and performance, single thread performance. If you do this, you need to have multiple register files, multiple fetch engines, basically multiple threads that you can execute from. And if your pipeline is deep, you need to have many threads to execute from. And also, you're making the trade-off that you don't care about single thread performance over here, right? If your single thread is really important, too bad. You're fetching instructions from that thread once every n cycles, where n is the length of your pipeline, the number of pipeline stages. Okay? So GPUs make this trade-off because they say the workloads that we have, graphics workloads initially, are highly parallel. I can actually partition my program into many, many threads, and I really don't care about the performance of a single thread because everything can be processed in parallel. So I design a machine that fits that sort of partitioning and that sort of trade-off. Unfortunately, GPUs also figured out over time that there are some critical threads that they need to accelerate, and this model doesn't work well for them. Okay, but that's the idea of fine-grained multi-threading. We're going to talk about GPUs in a few lectures. Well, we're going to talk about guessing the next fetch address in this lecture and tomorrow. Now let's talk about the problem. This is the slide that I mentioned that's going to show that, well, the next slide actually, is going to show that you really need to have a good branch predictor if you really want to design a high-performance out-of-order superscalar engine. So it turns out control flow instructions are frequent. Depending on your program, it could be 15 to 25% of all instructions, and the ISA, of course. And the problem is that next fetch address after a control flow instruction is not determined after n cycles in a pipeline processor. So the question is, what is n? So n cycles is the minimum branch resolution latency. We're going to assume an high-performance processor, out-of-order superscalar. So superscalar means we're fetching W instructions per cycle. That's the width of the superscalar engine. So if we're fetching W instructions per cycle, and if the branch is not resolved until at least n cycles, if you mispredict that branch, mispredict meaning that you actually go on the wrong path, or if you stall, what you're doing is you're really wasting n cycles times W instructions, right? Because the branch takes n cycles to resolve. You decided not to predict it, let's say. N cycles, you wait, and then you could have executed W instructions in each of those cycles, right? Fetched. So you're basically wasting n times W instruction slots. This is true if you stall or you mispredict the branch. Let's talk about misprediction because we don't want to stall, right? We've seen prediction methods earlier. So let's talk about the importance of the branch problem then. Assume that n is equal to 20, you have 20 pipeline stages. I should mention that this is minimum, right? In an out-of-order execution machine, n could actually go very large because your branch may be dependent on a long latency load instruction, and your branch may be resolved after 200 cycles or 500 cycles, right? But let's keep it constant for the purpose of this analysis. Let's assume that n is 20 and W is 5. You're basically fetching 5 instructions per cycle, 5-byte superscalar. And we're going to assume 1 out of 5 instructions a branch, which is not unreasonable, and also to make the math easy. And assume that each 5 instruction block ends with a branch. So every 5 instructions at the end, you have a branch, basically. Just to make the analysis simple. So one question is, how long does it take to fetch 500 instructions? I haven't given you complete information. Assuming your branch prediction is 100% accurate. Now, this is easy. If your branch prediction is 100% accurate, you have no mispredictions. And we're basically fetching 500 instructions, and we're fetching 5 instructions per cycle. So you divide 500 by 5, right? 500 divided by 5 is 100 cycles, right? Because, yeah, just to do it again, we're fetching 500 instructions, and in one cycle, we're fetching 5 instructions, and we're not wasting any cycles because our branches are perfectly predicted. So with 100% accuracy, we should fetch all instructions after 100 cycles. So there's no wasted work. At least the fetch IPC, assuming everything else is fine, meaning there are no dependencies in the program, etc., your IPC should be 5. 500 divided by 100. That's great. That's the ideal. Now let's make it 99%. If you're predicting branches 99% accurately, remember we have 100 branches in this program. based on what I said. We are fetching 500 instructions, 1 out of 5 instructions a branch. So we have 100 branches. 99% accuracy means that one of those branches is mispredicted. Now, what did we do? Basically, if one of those branches is mispredicted, for 20 cycles or n cycles, we're on the wrong path. So basically, for 20 cycles, we waste on the wrong path, right? On the correct path, we still need to fetch 100 cycles, right? Because we need to fetch these 500 instructions, except one of them is mispredicted. So 20 cycles, we go do some useless stuff. Now we've actually fetched all of those 500 instructions in 120 cycles because we wasted 20 cycles on the wrong path. Maybe not too bad. So we fetched 20% extra instructions, if you think about it, because instead of spending 100 cycles fetching, you're spending 120 cycles. That's not good for energy. And your IPC, assuming everything, all of the dependencies are good, IPC is 500 divided by 120. Not so good. So this was 5. Now 500 divided by 120 is close to 4, actually. Okay, we've lost some. But not as bad as we will lose if you actually you're 90% accurate. 90% accuracy is quite good, actually, right? It's much better than a random chance. We'll see how we get to 90% accuracy, if we can get to it. So let's take a look at, let's do the same example. 90% accuracy, what does that mean? We have 100 branches, 90% of them are predicted correctly, meaning only 10 of them are mispredicted. Only 10. We're spending 20 times 10 cycles on the wrong path, right? Because each branch misprediction costs us 20 cycles. And we have 10 of these, so we have 300 cycles on the wrong path, 200 cycles on the wrong path. And we still need to fetch on the correct path 100 cycles because we need to finish 500 instructions, right? So we're on the wrong path more frequently than on the correct path, right? So to be able to fetch 500 instructions, we're spending 300 cycles. And 200 of them are on the wrong path. Now, quickly, we fetched 200% extra instructions. And our IPC tanked to 1.6 bar. So instead of 5 IPC, we go to 1.6 IPC, instructions per cycle, performance, even with 90% accuracy. This is amazing, right? So this is why you should really keep the pipeline full, correct, and moving. Okay? So if you actually do this for 60% accuracy, you'll be very sad. 60% is still better than random luck, right? And there used to be a time when branch prediction was 60% accurate. Our machines were not as complicated back then. But 60% accuracy means that 40 of the branches put you on the wrong path. So you spend 20 cycles on the wrong path for each of those branches. So 800 of your cycles are spent fetching on the wrong path. You still need to fetch 100 cycles on the correct path. So you spend 900 cycles total fetching. 800 of them are useless. So you fetch 800% extra instructions, and your IPC is sad. 5 divided by 9 instead of 5. Okay? So this is why branch prediction is very important. This is why we're covering it. If people say branch prediction is not important, show them the slide. Okay? This slide puts the picture. This is why people actually try to optimize this heavily. Because if your pipeline is deep and wide, even 1% makes a difference in terms of energy and performance. And there are some workloads today where we're at 60%. Not so good. We have these heavy, good machines, let's say, that can figure out things. But on this important workload, it's at 60%, right? What do you do? So 60% is not good, 90% is not good. We want closer to 99% to 100%. The sad thing is 90% is not good, right? And we're going to have a lot of difficulty getting to 90%. Okay, so that's why branch prediction is important. Any questions on this slide? I love this slide. Anybody else love this slide? No? Okay, some people say, fine. Maybe you'll love it later. Sometimes it takes time to love something. Okay, so branch prediction, you've seen the idea basically. So I'm going to go through these like conceptual slides relatively quickly, but you need to guess the next instruction to fetch. You have a branch or instruction over here in your sequential instruction stream. The next instruction can be this one or this one. And we said already that stalling the fetch is not a good idea. This is what happens if you stall the fetch on a conditional branch in a simple pipeline, 5-stage pipeline. Okay. If you do branch prediction, and if you predict correctly, you, let's say, predict you're going to this instruction next, as opposed to this instruction. Okay. This could be a loop, for example, that you keep executing, and you fall out of the loop. That's the next sequential instruction, and this is the target instruction. So with branch prediction, even with simple pipelines, you gain significant performance improvements on this very short piece of code, right? That we didn't even completely execute, as you can see. So that's significant improvement. That's 33% performance improvement over here. Okay, but of course, the downside is misprediction penalty. This slide up for some reason doesn't work well. I wanted these to be red, but they're green. But basically, if you mispredict the branch, you need to flush the pipeline. You fill. So for example, in this particular case, we predicted that the next instruction that's coming after the branch is this add instruction, next sequential instruction, and we filled the pipeline with these instructions. Unfortunately, that's mispredicted, so we need to flush the pipeline and restart from the correct next PC, which is this one. So we basically waste time if you are mispredicting. It's still better than stall fetch, though, on average. Okay, so simplest way, we've already seen this. What is the simplest branch prediction mechanism? Always guess that the next PC is the same, the next sequential instruction, PC plus 4 in MIPS. That's simple. This is a form of next fetch address prediction and branch prediction, even though you can say this is a trivial form, because you always increment the PC anyway, right? That's what we did. So this simplest way may not be very effective, but you can try to make it more effective, right? So let me actually try to see if I can switch to this. I'm going to overlap the latency of this and this in the meantime, see if we can be successful. Because I want to give a quick example of this. So basically, you can make this more effective by trying to maximize the chances that the next sequential instruction is actually the next instruction to be executed. How can you do that? Compiler can reorder the code. So basically, software or compiler or the programmer can lay out the control flow graph such that the likely next instruction is not on the not taken path of a branch. Let's take a look at this with an example. Do you think this will work? What do I do? DocuCam? No, it's not connected. Okay. Okay, while he's connecting this, this is called profile-guided code positioning. This is actually employed in modern compilers. This beautiful programming language design and implementation paper talks about it. And modern compilers try to do this. Hardware can actually internally do this also, potentially. Intel introduced the idea of a trace cache, which basically reorders the instructions internally such that this sort of prediction becomes better. Oh, it's okay? Okay, I can switch to DocuCam. Thanks. And I need to stop sharing, is that correct? Okay, let's see. Okay, this is DocuCam. I'm going to just show a simple example with my favorite pink color. Okay, that's better. So basically, you can have code that looks like this. If X, so there's some branch over here that tests X. You execute a block A, let's say. So this is block A. Else, you execute block B. Sorry for my mess. Can you see this? Okay, good. So you can see this. I could have color-coded things. And then both of them reconverge at block D. I don't know why I call this D, but fine. So this is your sequential code, like this, and this is your control flow graph. There's a branch over here, which is this one. And then if branch is taken, this is a taken path, this is A. If the branch is not taken, this is a not taken path, which is else, this is B. Okay? And then they both converge. There's an unconditional branch at the end of one of them. So usually this one, unconditional branch to D, and this is sequential. Okay? So if you look at the layout of this code, you have the branch block over here. The next block is B. The next block is D. And A may exist somewhere else. Okay? Does that make sense? So this branch tests this, and these are the connections that you have actually. Okay? So this is your sequential code. Let's call this something. I don't know. I should have used a better terminology. X. This block X over here XBD is sequential. This is great if this branch takes this not taken direction more than 50% of the time, right? If this is more than, if this code layout is nice, if this is more than 50% of the time. If that not taken is used, or that not taken edge is exercised more than 50% of the time. In other words, if the branch is not taken more than 50% of the time, okay? In other words, if X is not true, right? More than 50% of the time. Now, if the opposite is true, let's assume that the compiler profiles this code, figures out how often this taken is true and how often this not taken is true. It's possible to do that. You can actually write a profiler. Your compilers actually are doing that already. It basically says, oh, I see 99% of the time branch is taken, and only 1% of the time branch is not taken. You figure this out somehow. This is called profiling. We're going to see this also. Compile time profiling. You could do that dynamically also at runtime. Then the question is this code layout good if your branch prediction mechanism is next, always predict the next fetch PC as PC plus 4? And the answer is no, right? Because if this is true, your program is mostly going through here. So when you get to this branch, your branch is not taken, even though you're fetching this next piece of code that's laid out sequentially, right? So if your branch prediction mechanism is next PC equals PC plus 4, you should really put A after X as opposed to B after X, right? And that's the idea, basically. That's the idea of this profile-guided code positioning. Somebody, it could be the programmer also, but somebody figures out the frequency of taken, not taken direction of these edges or branches, or taken frequencies of the branches. It's also called a taken frequency. And they lay out the code appropriately so that next PC equals PC plus 4 prediction works nicely. So how do you lay out the code? You need to do it this way, right? So you need to do a fix up, of course, at the end, right? So B needs to go here. And so the taken path needs to change, right? No, what did I do? Oh, sorry. Yeah, that's correct. So B also needs to go here. Okay. So basically, that also needs to be fixed, of course, right? I mean, you can think of this as, yeah, then you're testing X, but you really need to be perhaps testing not X, right? In this particular case. So basically, if not X, you go to, yeah. So you can think of this as you do B and A over here. Hopefully that makes sense. Kind of, maybe. So you could actually do this in the programmer level also by fixing your program, actually. So that's the idea, basically. So instead of having this code, instead of having this layout for this code, you actually use this layout for this code. Does that make sense? Okay. So that's what I wanted to say over here. So you could do this in any branch prediction mechanism. I'm going to close this if I can. What happened here? So you could do this in actually any branch prediction mechanism, as we will see in some of them. But it's very effective if your next PC prediction is PC plus 4. Of course, maybe I should have said this also, sorry. I should go back, stop sharing. We're still at DocuCam here, that's good. So if your probabilities, what's going on? This only works if your probabilities are nice, right? If your probabilities are not 99%, but more like 50% and 50%, unfortunately, there's no bias direction. So there's no good code layout. If your probabilities change, so if you profile, oh, sorry, what's going on? Okay, so that's what I meant. So if your probabilities here are 50% and 50%, neither of these is good. Okay, stop sharing also. Okay, thanks. Okay, so if your probabilities are 50% and 50%, neither of these layouts is good, basically. It doesn't matter what you do. Now, what could be worse is your profiling says this layout is better because when you're profiling, you get 99% over here and 1% over here, just like we did earlier. But at runtime, runtime is very different from profile. At runtime, it may be exactly opposite. This is 1%, and this, this is 1%, and this is 99%. Okay? So basically, if your profiling information is wrong, you may actually lay out the code this way because you think the branch is going this way 99% of the time, but it may actually be going this way 99% of the time at runtime. So this is the problem with profile representativeness, and this is a problem that plagues compilers in general. So your profile needs to be representative, essentially, for this to work. Okay, and this is a real problem, actually. If your profile is not representative, then your optimization, the optimization that you make at the compiler level or the programmer level, because programmer also has a profile in their mind potentially, may not work. In fact, it may backfire. Okay, so hopefully that's clear. Now let's see if we can handle this more gracefully. Did it work? No. Okay, it did work. Okay, so that's what existing compilers do or try to do. Okay, I'm not going to patch that, I guess. I tried to get rid of this, but okay. Yeah, that's what existing compilers try to do, to lay out the code such that it actually makes the branch prediction accuracy higher. Change the camera? Okay, how do we do that? Is it follow projector? Okay. No? Okay. Okay, it's very complicated, as you can see. This should be automatic also, right? I'm the programmer or user. I'm trying to deal with a lot of stuff. And if it was automatic, then it would be much better. Yeah. Now you can see the difference between Dataflow and at the ISA level versus microarchitecture level. Okay. So how else can you make this more effective? There are other ways. Next PC is equal to PC plus 4. Instead of laying out the code, which may or may not work depending on the profile representativeness, you might want to get rid of control flow instructions, right? This is always a good thing, actually, if you try to, not always, but this is a good thing if you try to get rid of control flow instructions or minimize their occurrence. So how do you do that? You can get rid of unnecessary control flow instructions by combining predicates and testing only once. Should I do that? Okay, I'll do that again. I'll construct another example, even though the latency of switching to this thread is very long, as you can see. Let's see, well, let's wake up. Okay, maybe it did wake up fast this time. So we go to DocuCam and is that okay? So what does getting rid of control flow instructions mean? Stop sharing. Okay. I'm going to give you a very simple example. But so, for example, you may have an if x and y and t and t. Basically, you're testing lots of things, right? M. And then you may actually have conditional, complicated predicates, right? Age is equal to, I don't know, 55. Well, I guess that way. And depending on your, of course, programming language, basically, you may be testing here 20 different conditions. This could be implemented as 20 different branches, right? You can have a conditional branch 1. You have some predicate computation, conditional branch 1. Some predicate computation, conditional branch 2. Predicate computation, conditional branch 3. So you're going to basically have conditional branch, 20 conditional branches to decide whether you execute this next code or go somewhere else. Or you could have a single big predicate computation that combines all of these and have a single conditional branch 1. So basically, you can combine these 20 conditional branches into a single conditional branch. This is a decision that to be made by the compiler or the programmer If your compiler is good, it can make that decision. Now the trade-off is, here you're predicting only one branch. That's good. And all of this code is sequential. So next, your branch prediction, next PC equals PC plus 4 is good because this is a big piece of code. That's all sequential. Here, you're predicting 20 different branches, and you may be going to different places, right? And your prediction may not be correct. So basically, this is better from a branch prediction perspective. But here, you may be executing some useless code to decide on the outcome of the branch. Here, if you're testing the predicates separately, you may be going out earlier out of some of the code. But here, you have to do all of the predicate computations and combine them only to a single one. So basically, there's a trade-off over here. But this is clearly better for the prediction accuracy of your simple branch predictor that we discussed. Okay, so that's the idea of combining branches. And compilers can do it, and the programmers can do it as well. So now, let's see. Cam, speaker. Okay. Is everything better now? Okay, good. Okay, so that was another way. Another way is actually converting control dependence into data dependencies. I'm not going to talk about this right now. If you have time tomorrow, we'll talk about this. This is called predicate execution. Most branches, you can convert them to data dependencies if your instruction set architecture supports it. And basically, this is a way of executing both parts of the branch, both paths after the branch. And then instruction set architecture provides support so that you can flush one path. This is called predicate execution. It's employed in some instruction set architectures, but not all of them. So it has not been as successful, let's say. Okay, let's take a look at branch prediction, always PC plus 4. We've already seen this, so I'm going to go through this quickly. Basically, if you have a misprediction, you need to flush the wrong path instructions. Okay, so that's a problem, clearly. So you need to have a way of flushing wrong path instructions. And wrong path instructions are costly, as we have discussed. So let's do a quick performance analysis, even though we did the biggest performance analysis earlier. So if you have a correct guess, let's assume no penalty. If you have an incorrect guess, let's assume you flush only 2 instructions. And let's assume that correct guess is 86% of the time. Assume that there's no data dependency related stalls, 20% instructions are control flow instructions, and 70% of the control flow instructions are taken. If you actually do the calculation, you will find out that your CPI with this information is 1.28, which is not bad, clearly. Basically, you have for 70% of the control flow instructions, for 20% of the instructions, 70% are taken. So you mispredict them, and you have a 2-cycle bubble, 2-cycle penalty on them. So you add the penalty to the CPI that you need to have in a pipeline machine. Okay. So I call this the probability of a wrong guess. Ideally, we would like to reduce this, but there's also the penalty for a wrong guess. We would also like to reduce this. So this is called the branch misprediction penalty. So if you want to improve branch performance, you could improve either one. So probability of a wrong guess is improved by doing better branch prediction. Penalty of a wrong guess for a wrong guess is improved by reducing the branch misprediction penalty. So remember, actually, when we looked at the pipeline processor, you can resolve the branch condition and target address early. We call this early branch resolution. And we added extra logic in the earlier lecture 13, actually, that Mohammed covered. This added extra logic earlier. If you could do this, that's great. But this has downsides, as we have discussed, right? We asked, this is a good idea. This could actually increase your clock cycle time. Okay, so if you're interested, you can take a look at that lecture. So it's important to think about these 2 terms, reducing the branch misprediction penalty. It's usually much harder. So reducing the branch misprediction penalty, especially in an out-of-order machine, is not easy. So you cannot do this sort of tricks easily in an out-of-order machine. In a pipeline machine, you could, but at the expense of clock cycle time. So now that's why we're going to focus on branch prediction. But never forget the misprediction penalty term. A lot of people forget that misprediction penalty term. As a result, they may actually make some not so great decisions. So let's talk about enhanced branch prediction. So I'm going to break it down into multiple things. So we would like to predict the next fetch address to be used in the next cycle so that we don't have any wasted cycles on correct prediction. This requires 3 things to be predicted at the fetch state, actually. One is whether the fetch instruction is a branch. The second is the branch direction. For conditional branches. I'm going to assume conditional branches from now on. and then the branch target address, assuming the branch is taken, predicted taken. So you need all three of them if the branch is taken. Let's take a look at branch target address. How do we actually get that? Because we want to get that while we're fetching the branch instruction, right? We're fetching this branch instruction. In the next cycle, we need a target address. If this branch is taken, we want that target address to be available at the end of this clock cycle. We need to know whether the fetch instruction is a branch and the branch direction. So the observation that helps us with the third one and the first one is target address remains the same for a conditional direct branch across dynamic instances. Remember, a conditional direct branch, you calculate the target address using PC plus offset, if you remember the MIPS ISA. And that PC plus offset is not dependent on a register, it's dependent on the instruction, which means that if you've executed the instruction once, you can store that address somewhere and remember it for the next use case, next execution. So that's the idea basically. And all modern machines do this. They store the target address from previous instance of a branch, execution of a branch, and access it with the PC in the fetch stage. While you're fetching the instruction, you're using the program counter to access the instruction memory. You also use the program counter to access a cache of target addresses called a branch target buffer, or branch target address cache in IBM terminology, to get the target address. This way you can concurrently fetch the instruction and get the target address. That sounds good now. And if you actually find some target address in this branch target buffer, that means that that's a branch instruction, right? Because you populated this branch target buffer with an address. So basically, a fetch stage is going to look like this. We will have a direction predictor that's going to tell us whether the branch is going to be taken or not. We will have this cache of target addresses or branch target buffer. We're going to use the program counter, which is the address of the current branch. I'm going to assume that this is a branch from now on. If it's not a branch, it's easy, as we will see. We're going to use the program counter to index both the cache of target addresses. If there's a target address associated with this program counter, we're going to get a target address and a hit signal saying that, oh, there's a target address associated with this program counter, which means that I've executed this branch in the past and I retained the target address over here. And this program counter is going to be indexed, used to index into the direction predictor, which is going to say whether the branch is going to estimate it or guess to be taken or not taken. Now, if the branch is not taken, or if this is a miss, then we're going to use PC plus instruction size, PC plus 4 in MIPS as the next fetch address. Because we don't know the target address, or we're predicting the branch has not taken. Right? Now, if the branch is taken, and if we have a target address, we're going to use that target address as the next fetch address. So this is your fetch logic, front-end logic. And we're going to make this direction predictor more and more complicated today and tomorrow. So let's take a look. Actually, we're going to start with some compile time mechanisms also. So more sophisticated branch direction prediction, we will see. So this part is fine, but we're going to hash or XOR the program counter with global branch history. This is actually employed in many processors. This exploits the correlation between branches. And we will see there's a correlation between branches in terms of predictability. And this actually made a huge difference when Intel built the Intel Pentium Pro, because they exploited this sort of correlation. And that actually increased the predictability of branches to 80 to 90%, let's say. So we're going to see that tomorrow. But let's finish this part first. So we require three things to be predicted at fetch stage: whether the fetched instruction is a branch, conditional branch direction, and branch target address. The third can be accomplished using a BTB. We remember the target address computed last time the branch was executed. The first can be accomplished using a BTB, because if the BTB provides a target address for the program counter, then it must be a branch, right? This could be accomplished in some other way, but I'm not going to talk about that. You could actually have some branch metadata bits in the instruction memory. The second is the thing that we're going to, let's say, obsess ourselves with. And a lot of people actually develop a lot of interesting algorithms for this. So this is what we're going to study. We're going to study some compile time static branch prediction mechanisms. Some of them you've already seen, actually. And then we're going to move to runtime and make things more sophisticated. In fact, we're going to use machine learning algorithms and more sophisticated algorithms. But let's start with the compiler time or static branch prediction mechanisms very quickly. So these are, we've already seen some of these, right? Always not taken. This is simple to implement. There's actually no need for BTB, no direction prediction, right? But the accuracy is low. In fact, it turns out 30 to 40% accuracy you get with this for conditional branches. You could, of course, try to optimize it with limited success. Always taken, no direction prediction, you still need the target address prediction. Better accuracy, it turns out, because most branches are taken, actually. This is empirically observed in many programs. Most branches are taken because most branches are loop branches. Because whenever you're executing a loop, you're looping back to the taken address, target address. You're not falling out of the loop, if you will, and loops are implemented that way. So always taken is a better prediction method if you're going to choose one of them. So backward branches are usually taken, and backward branch is a branch that has a target address lower than branch PC. So people have figured out that backward branches are loop branches. They're mostly taken. Some other branches are not necessarily mostly taken. So they've also developed the backward taken, forward not taken mechanism, which is actually slightly better than always taken. So basically predict backward branches as taken, others as not taken. This is also a static branch prediction mechanism because whether a branch goes backward in the code to an earlier, the target address is earlier than the branch in terms of sequential code, is a function of the branch itself. It's not a dynamic thing. So we talked about profile-based branch prediction. Let me cover this. The idea here is to be more sophisticated, basically. To use the compiler to determine a likely direction for each branch using a profiler. Profile the code, figure out whether a branch is going to be taken or not taken more frequently. And change the instruction set architecture, encode that likely direction as a hint in the branch instruction format. So each branch instruction is a bit saying that this is the likely direction that the compiler tells me. Now this is nice because now you can actually do the per branch prediction. So all of these previous ones are not per branch. They're basically global across all branches. Here, you can basically distinguish between branches. If the compiler said correctly that this branch is taken most of the time, you can predict that branch is not as taken. And if the compiler correctly predicted that this other branch is not taken, you're going to predict that not taken because every branch will be encoded with this bit. Now this is nice. Of course, the profile representativeness problem exists. If the compiler decided the wrong thing, well, too bad. You're going to do the wrong thing. Unfortunately, this changes the ISA, which may not be a bad thing, actually. Actually, all ISAs have this sort of hint bit today in the instruction format. All interesting ISA. And accuracy depends on dynamic branch behavior. So I'm going to use this sort of terminology today and tomorrow. But this basically looks at the execution history of a branch. In the first 10 instances, these are T's, the branch is taken, 10 T's, and then 10 N's. Here, there's a different dynamic behavior. The branch in the first instance is taken, and then not taken, taken, not taken, taken, not taken, taken, not taken. These are very difficult patterns for if you use one bit to encode a profile or taken or not taken direction for a branch. Because you can only encode one direction, taken or not taken, and regardless of what you encode, you get 50% accuracy in this case, right? Because the branch is 50% taken, 50% not taken. But you can see that these are actually quite predictable. Right? If you actually design something more intelligent that can keep track of the patterns in hardware, you can predict these almost perfectly accurately. And that's where we're going to get to. As we discussed, the accuracy of profile-based mechanisms depends on the representative of profile input set. So this one is interesting. In this case, 18 instances are taken, and then the remaining 2 instances are not taken. If the compiler correctly predicted that taken is the dominant direction, you would get 90% accuracy. If the compiler incorrectly predicted that not taken is the dominant direction, you'll get only 10% accuracy. So you can see how bad the decision can be, right? If a branch is biased like this. If you cannot find the biased direction, you will actually lose. Okay, this is where we will stop. Tomorrow, we will continue with more advanced prediction mechanisms, and hopefully we'll finish that. I'll see you tomorrow.